Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and get answers online, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. Today we will talk about the Fibonacci heap. I don't know how it will go because before discussing the Fibonacci heap, we need to first look at the binomial heap, and before the binomial heap, it is generally advisable to know how the ordinary heap works. So I don't know if we will get to the Fibonacci heap today or not. If anything, we will look at it next time. For now, let's briefly consider what a heap is in general. So essentially, a heap is a data structure that effectively allows us to maintain the minimum or maximum over a specific collection set. It is usually called a heap. Generally, when people talk about a heap, the simplest implementation is the binary heap, which is based on a binary tree. What it represents and what operations it generally allows. It has three main operations. Let's think about it. We will always retrieve the minimum, remove the minimum, and generally use a heap that allows us to do something with the minimum in a set. Therefore, we will have operations like getMin, which returns some kind of important data, then push some additional element and a struct that will remove this minimum from the set and necessary operations. Well, we will just throw some elements in there, 2, 3, 1, 2, 4, 5, 1, 8. And here is our set of all elements. Elements can repeat. And let's say we want to create a data structure that allows us to quickly retrieve the minimum from this set. Well, right now, the minimum in this set is 1. Then add some element to this set. Let's say I will take and add a 9 here and also remove this minimum from the set. For example, right now our minimum is this one, which is 1. We take it and remove it quickly. Now the minimum in this set has become 2. We can also remove it later, and now our minimum is 2, and we can continue to remove them with this minimum. Here we want a data structure that allows us to perform these operations quickly. Like if we do everything on an array, then each operation will, well, we can perform getMin in constant time, but this will have a complexity of n, because in any case we will need to go through all the elements. If sorting is done, then insertion takes on time, and deletion takes o1 time, or vice versa. This is if we use some arrays and simply store a sorted set of elements.
What can we try? We can perhaps try to put all of this into some kind of tree-like structure, maybe. This will actually be our binary heap. We will take a binary tree. A binary tree is a tree-like data structure where there are parents and the parents have children. This is indeed a binary tree. A binary tree actually means that each node in this tree will have no more than 2 children. For example, it is possible to have 1 child, and there may also be no children at all. That is 0, 1, or 2 children.
Want to become a great programmer? Subscribe to our Telegram channel.
And how can we store elements here? We will create a rule for this tree that the value in the parent, that is, the element in this parent, must be less than or equal to the elements of its children. Well, let's say something like this. 1, 2, 2. This is even worse for us. Why? Because here we have a parent, and its children have values greater than that of the parent. 2 is greater than or equal to 1. 10 is greater than or equal to 1. Another parent is 2, and its child has a value of 3. This is greater than or equal to 2. A pair can also be something. Let's say, if we place a 1, then that's already not visible. Because the smooth property of the heap is improved, the value in the parent must be less than or equal to the value in the child. Well, accordingly, this is for the minimum. If we are building a heap for the maximum, then we will have greater than or equal to the opposite here. This heap needs to be inverted. But we will always talk about the minimum because the heap for maximums is identical. The only thing that changes is this comparison operator, and actually the heap looks something like this. Well, accordingly, I won't fully explain how this heap works. You will cover that in the basic algorithms. Well, let me briefly explain what is happening here. The minimum will always be located at the root, right here in this node. Therefore, we can obtain it with a complexity of 1. We simply take the value from here, and that's it. This means that when we add an element, the complexity will be logarithmic. In fact, the same complexity will apply when removing the minimum and when adding an element. That is, here we will have the logarithm base 2 of n. How do we add an element? We take this element x and place it somewhere at the very end of the sequence. Then we simply need to push this element x up until the heap property is fully and completely restored. For example, let's say we want to add a 5 here. We hang it up and then just move it up to restore the properties. The 5, the 10 should be lower, so we will swap them. The 10 should be lower than the 5. 1.5 is already approximately fine. Well, that's it. We have restored the properties of the heap and added the elements. Since we have a binary tree here, and it is balanced if everything is written correctly, the complexity of such an operation will be no more than logarithm base 2 of n, because the height here will be logarithmic. And since we are simply moving up, in the best case we will go from the lowest leaf to the root. This will be the logarithm of n for the operation. For removal, we will do the opposite. First of all, we always remove this element, which is the minimum located at the root. We start pushing this element down in the opposite direction. If we look at the ports, it has 2 children, a 2 and a 5. The 2 is less than the 5, so the 2 should become the new value here, and we push our child down here. Do you want to become a cool programmer? Subscribe to our Telegram channel. 15. So there should be a 3 here. We pushed a 1 up here and removed it. So we removed the minimum also with the algorithms, because we essentially started. Well, there are some nuances on how to implement it, which they will explain to you using basic algorithms. Here, I have briefly covered the essence of this structure.
Want to become a great programmer? Subscribe to our Telegram channel.